Hello everyone. Let's continue our discussion with the switching threshold. So in the last video we came up with a task where we modified the PMOS sizes based on integer numbers of your NMOS and see what is the value of switching threshold. Okay, so basically we are trying to prove the robustness of switching threshold, and we'll try to plot switching threshold against how does the switching threshold varies with varying PMOS and NMOS sizes. Okay, so let's do that. So I have a spice simulator which is open over here. Okay, and we'll take the same circuit that we took in the past. So we have your PMOS, which is 0.375, your NMOS is 0.375, and based on that values, our W by L ratio is 1.5. Okay, so this is what we are going to do. We have your dot DC as so the same thing that we did in the past. Okay, so let's try to do a spice simulation. We have our spice simulator open. Okay, we will source the circuit file. Let me copy it out. Okay, we'll source it over here, .cir. Okay, we'll run the circuit. We'll set plot. The plot that is available to us is DC1. So let's do that. Okay, and let's see what are the plots which are available. So we'll plot out versus in. This is what we have done in the past, and this is the DC transfer characteristics of your CMOS inverter. So if you want to calculate the switching threshold, you just need to plot a line, a 45-degree line from the 0 point, and see where does that line intersects with this particular curve. It basically says that because whenever you draw a 45-degree line, its slope is 1, and whenever that particular point intersects for this particular curve, it basically says that is the point when your V in is equal to V out, and that's your switching threshold. Okay, so this was the DC transfer characteristics. In the meantime, what we'll do is we'll also try to do a delay calculation, a dynamic simulation of your CMOS inverter. The reason we are doing this is because this is the very good chance to identify what is the value of your rise and the fall delay of your CMOS inverter, and how does it vary with varying VMs. Okay, it's a very good point to start, and we'll be doing a whole course on dynamic simulation. So let's wait when we go over there. The dynamic simulation is a huge set of lectures, and we'll be covering it in a separate section of course. In this case, we'll just touch upon the dynamic simulation, where we identify what is the value of your rise and fall delay, and how does that vary with varying switching thresholds. Okay, so let's do that with the same configuration. We'll bring up one more spice deck. So this is how you do your dynamic simulation. Everything else remains the same, except the input that you provide will be a pulse. Okay, and your simulation command will be a transient. It's called a transient analysis. I'll come to the definition of transient analysis. So this is basically what it is called as. It's called the transient analysis, and the input that you will be providing, that is a pulse. A pulse is a waveform which is a function of time. So I'll show you what does a pulse mean. So what we'll do, let's try to show what a pulse means, or how does the definition of a pulse is being written into a spice deck. So if this is the pulse and if this is the spice deck, so this is what it means. If you have a pulse definition, it starts from 0. It starts from 0 volts. It ends to 2.5 volts. It ends to 2.5 volts over here. The shift is 0. So it says that your pulse is starting exactly at 0.0 at time unit 0. So if this would have been, let's say 50 picosecond, this pulse would have been started after 50 picosecond. Okay, so that's what a pulse mean. You have a rise time of 10 picosecond, 10 picosecond. You have a fall time of 10 picoseconds. Okay, and the pulse width is 1 nanosecond, and this complete cycle is 2 nanosecond. So this is the complete cycle of 2 nanosecond, and if you just try to calculate the pulse width, which is a 50% duty cycle pulse width, it's 1 nanosecond. Okay, so this is what your pulse means, and we are going to supply this particular waveform as an input to your CMOS and do a transient analysis and see what do we get. Okay, so let's do that as well. So we'll again bring up our spice simulator. Okay, and now we have the netlist present over here, so let's copy it. Okay, so we'll source the circuit file .cir. Okay, now we'll run it and we'll set the plot. So you'll see a difference in the previous spice simulations and this one. In this case, the set plot will tell you it's a transient analysis. Okay, basically says that we are doing a transient analysis. In the previous case, since we did a DC transfer characteristics, it basically says you it's a DC1 or DC transfer characteristics. In this case, we are doing a transient analysis, so it's called tran2. So we'll put tran2. Okay, and let's see what are the plots available to us. So we need to plot the input as well as the output waveform to calculate the delay. When you calculate the delay, it's basically 50% from it's basically a point at which your input crosses 50% to a point where your output crosses 50%. Let me show you that. So we'll plot out versus time, okay, and the input waveform. So this is what I meant. So it's not clearly visible. I'll make it visible. So this is your input and this is how your output switches. Okay, so if you want to calculate the rise, let's say we are going to calculate the rise delay. So this is your rise, this is your point when your output voltage rises, and you need to go to 50% of this particular waveform. So 50% is 1.25 volts. Okay, we'll zoom in. This is the 1.25 volts. We'll zoom in even more. Okay, and once you get that, you just need to click on this one. So this is your time axis, which is in nanosecond. This is your voltage axis. So if you want to calculate the delay, you just need to identify the difference between this point and this point. So this is your rise waveform. It's a zoomed in version of your rise waveform. This is the falling edge of your input waveform. So if you just click on this one, if you click on this one, or basically this is the way the SPICE simulator works, you just need to identify what is this point from the time point of view. You need to identify what is this point from a time point of view to calculate the difference, and that there you will get the rise delay. So let's do that. We'll click on this one. So this is basically 1.0144 on your x 1.0144 nanosecond. 10⁻⁹ is nanosecond. At y0 is equal to 1.25 or approximately equal to 1.25. Okay, so this is one point. We'll click on the other one, and you'll get the other point 1.16277, and then take the difference between this one, and this will give you a rise delay. So let's do that. So we'll clear this. 1.16277 minus 1.01446. So 0.148 or 148 picosecond is your delay. So that's your rise delay. We'll do the same thing for fall delay as well. Let's close this ones. For the fall delay, you need to find out a point at which your output falls. In this case, the output falls at this point. Okay, and this is when your input is rising, and we'll need to take the 1.25, the 50% of your input voltage waveform, and let's see what do you get as the fall delay. We'll zoom in 1.25. We'll zoom in even more. Okay, we'll zoom in even more, and let's see what do we get. And we'll follow the same strategy. We'll click on 1.25 at over here. So your x0 or the x-axis shows as 2.00486 nanosecond. Okay, same thing. We'll click over here. We'll get 2.07653 nanosecond, and then calculate the difference between it. So we have our calculator. We'll take 2.07653, okay, minus 2.00486, and this comes to about 71 picoseconds or 0.01 nanosecond. So this was about how do you calculate the rise and the fall delay for the inverter. And let me jot it down. So for a value of WP by LP equal to WN by LN, this is the rise delay and the fall delay that we just calculated. It's 148 picosecond is the rise delay, and the fall delay is 71 picosecond. And you draw a line, you draw a 45-degree line from 0 to 0, and this is the point at which it intersects. Okay, and if you zoom in over here, so let's zoom in over here. The quick way to do is click on this line and just zoom in. So if you zoom in over here, if you see, this particular is the point where your this curve is intersecting with the 45-degree curve, and that particular curve is somewhere at 0.9. It's somewhere lying at 0.99 volts. So your switching threshold is equal to 0.99 volts. Your rise delay is 148 picosecond. Your fall delay is 71 picosecond. Okay, similarly what we'll be doing is we'll be doing the same thing for all this set of combinations. I know it's a tedious work, but we need to do it, and we'll plot a table specifying what is the value of your switching threshold, what is the value of your rise and fall delay, and eventually deduce a conclusion about the CMOS inverter robustness. So let's try to do all this in the next video. Thank you.